Okay, students, today we'll be studying the quality factor or the Q factor of simple harmonic motion. This is going to be very important in your circuits also. I'll draw the analogy later on in my next videos, but for the time being, let us first understand what the quality factor or the Q factor is. By definition, the quality factor is 2 pi times the energy stored in one cycle in a harmonic oscillator divided by the energy lost in one cycle. So you can understand that I'm talking for a damped system, because if the system is free, if it is free oscillation, then there is no energy lost. So the quality of that system is infinity. So you can see by the definition, the quality of that oscillation depends on the energy lost. If the energy lost is less, that is, if damping is less, then the quality of that oscillation is high. And if damping is large, because energy lost in a simple harmonic oscillator is only due to damping, if energy lost or damping is more, then the quality of that oscillation is less. In other words, you can say it is the quality factor tells you the number of times the wave is going to oscillate before its energy decreases appreciably. So see, if the system is oscillating like this and it oscillates, let's say, for 100 times before its energy reduces to a considerable amount, then the quality factor is it is telling you how many times it is oscillating, full oscillation is taking place before its energy is getting reduced considerably. But let us say if the damping is very large, maybe the system would oscillate say 20 times and the energy would go down considerably. In that case, the quality of oscillation is going to be very low, since the damping or the energy lost in one cycle is going to be very large. So if the energy lost per cycle is going to be large, the number of times it is going to oscillate would be low, and that would mean that the quality of oscillation would be low. So damping large, the quality of oscillation is going to be low, and vice versa. If damping is low, then the quality of oscillation would be very high. So by definition, remember, the quality factor of any simple harmonic oscillation is given by 2 pi times the energy stored in one cycle divided by the energy lost in one cycle. So let us derive the expression for quality factor. The approach that I have taken is not very rigorous, or maybe it's not very accurate, but it would serve the purpose. We can do it in different ways, but I have chosen a way which would be very, or which would be much easier for you guys to grasp. So if you remember, for underdamped case, the displacement was e to the power of minus bt a cos omega t plus b sin omega t. You remember I told you this is the oscillatory part and this is the exponential decay part. So it is oscillating, under damped case, it is oscillating, but the amplitude is exponentially decreasing to 0. So if you remember, this is the oscillatory part and this was the exponential decay part. Now this equation can equally be written as c e to the power of minus bt cos omega t plus phi. So I have combined all of this to a particular single constant c plus a phase constant phi. So cos omega t plus phi. How can I write this? I've just written it like this. You don't need to show it in your exams, but this is for your clarification, that I can really write this as this. So c cos omega t plus phi, if you expand cos omega t plus phi, c cos omega t plus phi can be written as c cos omega t cos phi minus c sin omega t sin phi. So you can see this. So c cos phi is a, c cos phi can be written as a, and c sine phi can be written as minus of b. So I can write this a and b in terms of a single constant c and another constant phi. So I'll be writing not in terms of this but in terms of this, the displacement. So the displacement of a damped harmonic oscillator can be written as this. So this is the displacement. So remember, this is the oscillatory part, cos is the oscillatory part, and e to the power of minus bt is the exponentially decreasing or decaying part of that amplitude. So the energy stored in the oscillator, see, we need the energy stored in one cycle. So the energy stored in the oscillator is, the energy stored in time t, let us say, is half kx square. This was the potential energy, right? So k, you remember, k was equal to, or omega naught square was equal to k by m, if you remember. Then k was equal to m omega naught square, where omega naught was the natural frequency, and x square, so this is x, so x square becomes c square e to the power of minus 2bt cos square of this. So this is the energy stored in the oscillator. Remember, this expression is the energy stored in the oscillator in time t. This is in bracket t. So I'm sorry that I'm not clear in this case. This is E bracket t, that is energy stored at time t. This is the energy stored. Now what is the energy lost in one cycle? So if at the start of the cycle the energy stored is ET, and if capital T is the time period of oscillation, then what is the energy lost in one cycle? Because what is the time after one oscillation? It is T plus capital T. So this is the energy at time T plus capital T, that is after one oscillation, and this was the energy before the oscillation started. So what is the energy lost in one cycle? That is the denominator. The energy lost in one cycle is the energy at start of the oscillation minus the energy at the end. The energy at the end is T plus T. So just in order to get this value, energy at T plus T, I'll substitute at every place small t by small t plus capital T, because this is T plus, if this is the energy stored at time t, then what is the energy stored at time t plus capital T, that is after one oscillation. So t is the time period. So Et plus capital T becomes, all this remains the same. Instead of small t, I'll write t plus capital T. So this will become e to the power of minus 2bt. Another factor will be there, because t will be replaced by small t plus capital T. So you have this, and again t would be replaced by t plus small t plus capital T. This would be small t plus omega capital T plus phi. Now what is cos omega t plus cos omega capital T plus phi? You remember, omega into capital T is 2 pi, because omega was 2 pi by t. So basically this is 2 pi. So a cos of omega t small t plus phi plus 2 pi can be written as cos of omega t plus phi cos 2 pi minus sine of omega t phi plus phi sine 2 pi. This is 0, and cos of 2 pi is 1, so it is cos omega t plus phi. So it is cos omega t plus phi. So I can write this as omega t is 2 pi. I can write this as straight away cos square omega t plus phi, because 2 pi is not going to make any difference. This omega capital T is not going to make any difference, because this is the same as this is the same as this. This is the same as this, and this is nothing but 2 pi. So I have this square, I have this, so this is cos square of omega t plus phi. So this is the energy at time t plus capital T, that is end of one oscillation. So now one more manipulation. Now this is, you can see, this is half m omega naught square c square e to the power of minus 2bt cos square of this is nothing but Et. You can see half m omega naught square c square e to the power of minus 2bt cos of this. Just this extra term is there. just this extra term is there for et plus t. So it is, I can write it as et, that is at time t, e to the power of minus 2b capital T, this term. The rest is same as et, small t. Now for small b, because you remember I am doing underdamped case, so the damping is small. For small b, I can expand e to the power of minus 2bt, or e to the power of x can be written as 1 plus x square. I can neglect the higher order terms. I can approximate e to the power of minus 2bt as 1 minus 2bt, that is 1 minus x plus x square by 2. So neglecting the higher order terms, it is 1 minus 2bt. So e to the power of minus 2bt over here can be approximated as 1 minus 2bt for small b. So I replace this. So what is et plus capital T? It is et into, I replace this by 1 minus 2bt. So it becomes et minus 2bt into et. So just this is the energy after one oscillation. This. So what is the energy lost? The energy lost is the energy before the oscillation started or at time t minus the energy after one cycle. That is this, et plus capital T. So if you subtract this, you would get the denominator as 2ebt, and in the numerator it is nothing but the energy stored in one cycle. So this is the energy stored in one cycle is nothing but et, and the energy lost in one cycle is, this cancels out, it is 2etbt. So this e and e cancels out, I have 2 pi by 2 bt. So I can write t as 2 pi by omega. So 2 pi gets cancelled, omega goes up. So I have omega by 2b. So what is the quality factor? Finally, the quality factor, we have found the expression for the quality factor. This is going to be very, very important. The quality factor of an oscillator is omega by 2b. So you can see the damping is in the denominator again. So if the damping is large, huge damping, that is energy is lost in the oscillation, then the quality of oscillation is poor. And if the damping is low, that is energy is not lost that much, then the quality of oscillation, that is the number of time it will oscillate before the energy reduces considerably, is going to be very high if b is small, and vice versa. So this is the quality factor. Next we'll be doing sharpness of resonance. Thank you.